Sir, I think we can start. Um, I just came to know that some of the students have registered. They have this aptitude test from 3:30 to. So let us see how many turn up. But let us start, sir.
Okay, okay, ma'am.
Yeah, sure, sure.
Me,
Okay.
sir. Yep.
Yeah.
Yes, sir.
Okay, so very good afternoon, faculty member and dear students. So, welcome, a very warm welcome to you all to this SOA weekly academic lectures. Now, so this is lecture number 31, and so for lecture number 31, we have a wonderful person to give a talk on the topic named shallow learning, a non-iterative for feed-forward neural network. And uh, to deliver this topic with us, we have Dr. Parashjyoti Borah. He is currently working as an assistant professor in the Department of Computer Science in Indian Institute of Information Technology, Guwahati. So Dr. Borah is previously working as an assistant professor in the Department of Computer Science in SOA, and he did his PhD in computer science from National Institute of Technology, Arunachal Pradesh. And his research interests include machine learning, pattern recognition, data mining. He has also published 13 research articles in the international journal and conference proceedings. So Dr. Borah has reviewed various research articles in high impact reputed international journal and of his field of interest. So now, so that is what a brief introduction to Dr. Borah, but the Dr. Paras that I know is a very good human. So now I would like to welcome Dr. Parashjyoti Borah to start his presentation. So Paras, sir, now you can start.
Okay. Thank you, Divya sir, for the kind and nice introduction. Thank you, everyone, for joining. And it's my pleasure to have this opportunity. I'll directly go for sharing my slides. My screen is visible, sir?
Yes, sir. Absolutely.
Okay. Okay, today I am going to discuss the topic I have chosen for today's webinar is shallow learning, non-iterative feed-forward neural networks. So nowadays, we often hear the term deep learning, deep neural networks, and everything deep. So in deep, we have seen so many applications also. It is very efficient, but along with the this one performance efficiency, deep learning comes with some extra costs, such as high training cost, high you need to have some good configuration PCs, so like that. But in some cases we do not require that much of a high computational algorithms also. Sometimes a simple shallow kind of computational algorithm also work for some purpose. So in those cases, if we want to deploy deep learning, so it will be unnecessarily we are costing some computational overhead and some other resources we are unnecessarily using. In those cases, so we can use shallow learning because they perform very well. So that is why, and we have seen in most of the webinars, we have seen that there are so many applications like automated vehicle driving or many things in using deep learning, machine learning, or AI. We have seen so many applications. So we have seen those applications, but many of us we do not know what is happening inside. So I have picked some very simple yet very powerful algorithms which could be understood very easily and which could be implemented very easily. So I'll try to cover that also. And okay. Okay. So for that, I'll start with ANN. So we are all familiar with ANNs by this time, because nowadays these ANNs, machine learning, AI, all those things are very popular. And when we talk about machine learning or AI or data mining, we everywhere we get these ANNs. So basically, what is ANN we know, but still I'll briefly try to brush up. So ANNs, we know, artificial neural networks that are biologically inspired computational networks. So it try to emulate human brain. So, but it is not possible to emulate exactly what our human brain. I mean, the complex processing of our human brain. It is not very easy to emulate in computers or in machines, but still we are trying, and we are progressing also. So we started with some very simple neural networks. I mean, the researchers started with very simple networks. Now we have moved on to deep neural networks. So again, now spiking neural networks are coming, and many neural networks we have seen in Tesla. They are using some different neural networks. The structure is very different. So this ANN field is still evolving, but still we need to understand the basic. Then only we can work on the algorithms. We have seen many applications which uses those algorithms, but to work on the algorithm to make the algorithms more efficient or more suitable for specific applications, we sometimes need to modify the setup of the algorithms, or modify the principles of the algorithm. So in that case, we need to have the basic idea how the algorithms work. So this is in the figure. We have seen a simple neural network. So the first one at the leftmost layer, that is the input layer. So where we feed the input. So when we talk about input, so it could be any data, any sample that is consisting of some features. In this case, in this very specific diagram, we have three neurons. We can see three circles in the input layer. So that means the input that we are going to provide to this neural network, that has to be of three features, not more than that or not less than that. If it is less than that, we can use some padding or some other techniques. For if it is more than that, then we can reduce it. We can select three very representative features like that. When we talk about this basic kind of structures, so this three feature input we can provide to this neural network, and through this input layer will provide it, will feed the input to the neural network, and it will go through two different hidden layers. So in the first hidden layer, it will process something, and it will digest, and it will give some output, and that output will be fed to the next hidden layer too. Next hidden layer, it will be the input from the input layer will be, sorry, output from the input layer will be input to the first hidden layer. Then output from the first hidden layer will be input to the second hidden layer, and in this case, the output from the second hidden layer will be input to the output layer. And in this case, in the output layer, in the simple diagram here, we have only single neuron. But in some cases, we might have more than one neuron. When we talk about multi-class problems or some other kind of multivariate problems, then we can use more neurons in the output layer. So how when we talk, we have seen the structure. Now we have to train the neural network. So when we talk about training a neural network, so the key feature of traditional ANNs, so it is the iterative learning scheme. So we start with some initial guess for the weights, then we try that weight in all the connections, then we see the output, how the output is coming. If the output is good, then it is fine. Again, we'll try to improve the weights based on the output. Based on the current input, we'll go back and we'll try to improve the weights. Then again, we'll see the output. Again, it will come closer to the uh, target output. Like that, we'll keep on iterating. Iteratively, we train the model. Okay. So in that case, we use iterative learning backpropagation technique. Now, so on contrast to deep neural structures, where we have so many hidden layers. So deep neural network actually consists of hidden layers, many hidden layers, and we have different classes of deep neural networks nowadays. So in contrast to that, we have another kind of powerful ANN technique that is called single hidden layer feed-forward neural networks. So where we have single hidden layer. In this diagram, we have seen two hidden layers, but in SFLN we have single hidden layer. So we'll see some examples and we'll see some algorithms also. So, but here when we talk about training the model using iterative backpropagation scheme, so it has some weaknesses or disadvantages. So one such weakness is, so there might exist some local minima in the error surface where we try to which error means the error that we try to minimize. We try to reduce the error and we try to update the weights, and we try to get closer as much as closer to the target output. Then in that case, we might be stuck in some local minima when we use iterative scheme. So that is one very common issue in iterative learning. Another is slow convergence rate. So basically, we start from somewhere and we converge to the solution. We slowly go to the solution, move towards the solution. In that case, sometimes that convergence rate is very slow. So that means the training might take a little longer than normal. So that is one issue. Another issue is sensitivity to learning rate setting. So how we set the learning rate, that is also one important factor in training the neural network. If we do not set it properly, then what will happen? Sometimes we might oscillate around the solution. We might never reach the solution. That kind of situation also arise. So when you implement using iterative scheme in ANN, then this kind of issues you might face. So what alternative we can have? We can have one alternative, as we are talking about here, this SLFN. So SLFN means that single hidden layer feed-forward networks. In those cases, what we can do, we have input layer, we have one hidden layer, and we have the output layer. So in those cases, we have two set of links from the input layer to the hidden layer, then hidden layer to the output layer. So one set of links we can randomly update the randomly fix the weights for one set of links, and the next set of links we can use some methods to get the optimum or get the best possible solution for the for the weights of the from the hidden layer to the output layer. So that is one solution. So basically, I'm going to discuss this kind of structures or this kind of methods. Then we have seen the weights of one set of link we have randomized. The weights of the next set of link we consider as the solutions to be found. Okay, that for that we use least squares method, and that is closed form based. So we'll see that also. So this is one very simple structure of single hidden layer feed for neural networks. Okay, so here in this case, the input layer has two neurons, and the output layer has one single neuron, and hidden layer have some neurons, that is more than two. Now we have two set of links we can see from the diagram also, from the input layer to the hidden layer. So sorry. So this is one set of links. These links we are going to randomize. We are going to, sorry, this thing is not working properly. Anyway, and this we are going to find a solution. For finding the best possible weights for these links, we are going to solve some problem. So that is what we are going to do. Okay, so this is the problem in hand for this kind of neural structures and this kind of methods. So for this, we'll take help of some specific yet very popular and very powerful algorithms. One is random vector functional link network, and another is extreme learning machine. So these two are very commonly used single hidden layer feedforward network. Okay, we'll start with RVFL. In short, RVFL we can say, and full form is random vector functional link network. Okay, this is one of the popular supervised learning algorithms. Okay, in machine learning we have two kinds, basically two kinds. Nowadays, some other kinds are coming up like reinforcement and semi-supervised, and many things are there. So in the starting, we had supervised and unsupervised. So this falls in the category of supervised, and we can do some modifications to make it unsupervised also. So anyway, we'll see the supervised one, the classical one. So in this algorithm, so we can use to solve this algorithm, we can use to solve regression problems as well as classification problems. Okay. Some of the properties of RVFL. So existence of direct links from the input layer to the output layer. Then it is an SLFN. Then it is a closed form based solution that first assigns random widths to the links from input to the hidden. Then hidden to output is found by solving some problems, linear equations. Okay, that we'll see. So this is the structure. So in this structure, it is a RVFL structure. Okay, so in this structure we have input layer here. This is the input layer. These are the neurons. We have as many neurons we want. We can put it here. Then this is the hidden layer, and hidden layer is synonymously called enhancement node in case of RVFL. In case of specific to RVFL, we call this hidden layer as the enhancement nodes. Okay, so if we leave apart these red colored lines, then we'll see this is the input layer, this is the hidden layer, and from input to hidden layer we have different connections. Okay, then from hidden layer to the output layer we have again some connections if we do not consider the red colored lines. So that is similar to a traditional ANN. So we have links from hidden input layer to hidden layer to output layer. But in case of RVFL, what we have some extra links from input layer to the output layer, these links. So we have these links also in case of RVFL. So there are some advantages of having these links. So this is the basic structure of RVFL. Now we'll see this this technique or this neural network. Mathematically, we'll try to see how we can solve, because if you do not see the mathematics behind this, then we cannot implement it, or we cannot modify according to our requirement. We will not know what is going on inside the algorithm. You might get libraries if you want to use this algorithm, but if you want to understand, it is very simple, but you have to follow some mathematics. Now for this for understanding, so we are going to use some notations. Okay, so we'll see one by one. First is so xi. So I have represented this vectors and matrices in bold phase. Okay, this x you can see a bold character. Whenever you see one bold, then you will automatically identify that this is a vector or matrix. So smaller cases are vectors, and upper cases are matrices. So in this case, xi is a vector. It is a single input. Like suppose I have one input 1, 3, 4, 7. Okay, this is the input. Suppose this is the input to the neural network. In this case, we have how many features? 4 features, and we are going to feed this input to the neural network. In that case, we need to have 4 neurons, because as we are considering 4 features here, that means 4 columns. So we are going to use 4 neurons in the input layer, like that. But this vector, this is a row vector. So we are considering all the vectors as column vectors. So we can take transpose of it, then it becomes a column vector. So ultimately it will look like this. Okay, so this is what xi is, and it is from r to the power n. That means xi is a vector, simple, a single, data sample, which has n features. In this case, in the example that I have shown just now, in that case, n was equal to 4. Okay, we had 4 features. Now, for representing it generally, we are considering n here. N could be any number, 4, 5, any number. It may be thousands in case of image. So that depends upon the problem. Okay, now this matrix X, this is the arrangement of all the vectors one by one after the other. Okay, they will one vector represents one sample, and X is the data set that consists of all such vectors. Okay, we'll arrange it in a matrix form like this. Then for xi, it is an input. So as we are I mentioned that it is a supervised learning, so we need to have some target. We need to have some target so that we can find out the best possible width, so that we can modify the width to reach some target. So that target corresponding to the input xi is yi. Okay, this is not a vector. This is a simple single. This is a scalar basically. So in the example, suppose this was the example. This is xi. Suppose yi could be in classification. Yi could be 1 or -1. Suppose this is the class level. Okay, and when we arrange in the data set, how many samples we have? We have m samples, and when we arrange them in a vector, then it will be this y is a vector of the target values. Okay, for we have arranged it x1, x2, y1, y2 like that till ym. So there, the y is a vector that consists of the target values for the input variables or input samples. Now weight. Now for this case, suppose this is the weight. These links will have some weight. So this might be 1, 1, and this could be m, l something. Okay, so all the links will have some specific weight. So for one neuron, how many weights we will have? We'll have, if we have n neurons in the input layer, for in this case 4 neurons, suppose, how many links are going to this neuron in the hidden layer? So you can see there will be 4 links. That means one weight vector for the jth neuron. This is the first neuron. This is the second neuron in the hidden layer. Like that, this will be the lth neuron if we have l neurons in the hidden layer. Okay, so for the jth neuron, we will have this weight, and how many links will be there to the jth neuron? N. If we have n as the number of features in the input, then we'll have n such connections to that specific neuron. So in this case, we'll have 4 because we have considered 4 neurons in the input layer. So like that we can arrange. Okay, so this is for one specific hidden layer neuron. Okay, this weight is for one specific hidden layer neuron, and we can arrange if we have l this kind of neurons in the hidden layer, then for each and every hidden neuron we'll have one single this kind of weights. Okay, so when we arrange all of them, we get a matrix that is W, capital W, and that is the arrangement of all the weights. All the weights in this W is we are considering this only for this input to the hidden layer, and this W is we are going to take it randomize. We are going to randomize this W. Then after that, if you want to consider bias to the neurons, to all the neurons bias, then for one neuron, jth neuron, Bj is the bias. And when you arrange for L neurons in the hidden layer, okay, then it will be a vector b, and it will be in r to the power l. That means l, it is a vector that has l real values. Okay, l number of real values. Then we all know inside a neuron we use activation function to achieve non-linearity or to make it digest. I mean to get some processed output. We use some activation function. Here is the activation function. To the activation function we are giving x, that is that will I mean feed through the input layer. W, that is associated with its connection. These are connections. Then B, that is the bias. Okay, in some cases we do not use a bias at all. So the activation function will process this input, and it will give us the output from the hidden neurons. Okay, now output from the jth hidden neuron. So it is HXI. So it is the arrangement of, I mean, all the output from all the neurons in the hidden layer. So we have how many neurons in the hidden layer? We have L neurons in the hidden layer, small l. So all outputs will be arranged in one this one vector, that is HXI. And for all the inputs, this is for XI input, single input. For single input, we have how many, I mean, output from the hidden layers? L, because L neurons are there. For M inputs, X1 till XM, so we'll have a matrix that is H, and it is the arrangement of all the outputs from the hidden layer corresponding to the whole data set. Okay. So this is how we can arrange, and now we know this is regarding this links from the hidden layer to the input layer to the hidden layer. And what about the direct links? Here we do not have, in between we do not have any neurons or any layer between the input layer and the output layer. In that case we do not have to pass it through any activation function. That is why this is for these connections, and this X is for these connection, red colored lines. And why we are using directly X, that is the input matrix, because we do not have any hidden layer in between. Then we have augmented H and X, and we are forming a matrix, data matrix, that is D. So far we know what are the notations and how we have found them. And till here we have processed, till here this part, the whole thing we have seen already. Now what about these links? These links from hidden layer to the output layer, these links. Okay, so for these links we'll also associate some weights. Yeah, is there any questions? Okay. Anyway, now these weights, for the connections from hidden layer to the output layer, we consider beta. For the jth neuron from the hidden layer, we consider beta j. And when we arrange all these links, and when we arrange all the weights from these links, we get a vector that is beta hx. Now let us see the optimization process, how it is done. Now if you see, so this D, basically it is nothing but the matrix that we have formed here. So that means by processing, after processing in the hidden layer and augmenting the direct links, we get some input to be fed to the after this stage we get something to be fed to the output layer. So D is nothing but this D. So far we have arranged it, and this D could be directly fed to the output layer. And in this simple structure, we are considering only one single hidden, output neuron. So this D will be the input to the output neuron now. And associated for all the associated link, we have this beta as the weight vector. Okay, that means what happens? We know that along with the input, we multiply the weights d beta. This is the, this is the processed input to the output layer. So that is why after this we should get y. Okay, after this we should get y. Y is the target. Okay, y is the target, and when we multiply this input along with the output, and we do not pass it through any activation function, and we should get the output directly. In this case, what happens? Sometimes we might not get the exact output, that is the target output y. So what we are going to do here, we are going to minimize this. Okay, we are going to minimize this. So this means we are, from here we can get d beta minus y is equal to 0, right? So it should be 0, but if it is not 0, then we are going to consider the minimum value. So basically we are going to minimize this value. But sometimes what happens when we try to minimize this, so this could be positive, negative value we can get, and we can get some situation where positive, negative is equal to 0 could be the minimum value, but that is not the actual minimum value. So we want to use the square of this. So we are going to use the square of it. That means we are going to use not only this, we are going to not only minimize this part, square of this we are going to minimize. So that gives us the first term of this optimization problem of RVFL. Okay, and this is for this is called regularization. In the original optimization problem, this part was not there. Okay, we'll see some example without this part. So why this is used to optimize along with minimize error, we are going to optimize the model complexity. So in details it will not be possible to cover, but consider that we are trying to minimize the beta value also. So we are basically we are going to minimize this part. This is the cost function for RVFL, and this is the structure of the RVFL. So this is X. X is going to the hidden layer, and it will form H here along with B, and we are assigning some random weights here. Then after processing in the hidden layer, it will get H here, and H will be multiplied to H will be multiplied to this beta H, and X is also here. It is coming directly to your output layer. So here it will be something like this, and this X will be multiplied, and this will go to the, these two things will go to the output layer, output neuron. That is what this is. This is what we are getting here. So now we know that from our mathematics, we know that if we want to find some optimum value, then we can differentiate and we can equate it to 0. So if we differentiate this optimization problem and equate to 0, then we get this. This is just simple differentiation. So it is called partial derivative, but we have only one unknown. This D is something that is fixed, that is constant. It is the data matrix. Y is the output vector, so it cannot be changed. C is some constant. This acts as the trade-off between this part and this part. Okay, this part, this is the empirical loss, and this is the structural loss. So which one you want to give preference? By changing the values of C, you can put different weight on these two different parts. Anyway, so ultimately what we are going to do, we are going to in this case we have only one unknown thing, that is the beta, that is a weight vector to the output neuron. So we are going to differentiate this expression with respect to beta now only, because all these are known and all these are constant. Okay, so when you differentiate, then we get this equation. Now this is simple differentiation. After that, this is simple mathematics. What we are doing here, we are considering the terms associated with beta in the left hand side, and that is not associated with beta, that is on the other side. Now when you solve this equation, we get beta is equal to this is the inverse. Okay, this is the inverse. So this is simple mathematics. I do not think there will be any problem understanding this. And this is the solution. This is the solution that we have to do, that nothing else. So here we know that C is some constant, C is greater than 0, and it is a constant, it is a scalar. As I have told you that all the vectors and matrices are used with a bold face, and C is not bold face, so it is a scalar. So it is a scalar. So it as C is a scalar, so here T means, this T means transpose. So D ka jo T hoga when you differentiate matrices, so we get this matrix differentiation. If you study it, and you'll understand this. Ultimately, we get this solution. So some matrix multiplications, and why this I came, because we are left with only C if you solve this equation, but C is not a matrix, because we are going to add C with some matrix. So we are considering some identity matrix. So whatever you multiply to the identity matrix, and I mean this will keep the balance, and we can this made the compatibility to perform the arithmetic, matrix arithmetic. So now this is I mean the basic things. So if you want to implement this, these things you have to know, and you can modify on this, and it is very easy to implement. I have shown you, I'm showing you this Matlab function, how to implement. So this is the function, these are the input. X is the matrix, data matrix. For a image, you can convert the image to some I mean matrix form. And this is the target, and this is for testing. This is a test matrix, test target, and this is the parameter C, and this is the number of hidden layers. Okay, so this much we have to pass to the function. Now you can use different programming language also. It is very easy to implement this. Only this much of code is required. Of course, there are some more things into the algorithm that I have not shown it here. So if you want to, I mean, incorporate all the things, then you have to do a little bit of study. Then you can implement it. Now we are getting the size here. Now this wvec or wmat, whatever variable you want to use. So using this function, we are randomly assigning some value. Now this function will do what? This function will give us a matrix that has n rows and l columns. Okay, so why n rows? Because w should be in the notations I have shown. This w will have how many this kind of w's? Omega, actually this is omega. So l omegas, and each omega is having n number of your features, or sorry, in n number of rows. In that case, the matrix W will be of dimension. This here I have used capital L, but in the notation I have used small l, so I'll keep it like this. So W vec is a matrix that is of dimension n by l. Okay, and all the I mean entries in the matrix will be randomized, randomly initialized, and that will be fixed. We are not going to update anything, or we are not going to use any iterative scheme, so that we can update the links. First we'll see the output for some random value, then again based on the output we again try to improve the I mean weights. We'll update the weights. Like that we'll not do. We'll randomly assign it and we'll keep it fixed. Then after that, similarly, bvec is this is the variable, or it is a vector. and in this case it will be a vector because the number of columns here is 1. So some random values. Okay, so this is B. Vivek. So these are the random initializations done. Then we are performing some activation function. In this example, I have used sigmoid activation function. You can use some other activation functions also. So I have passed these values. Then that will give us the matrix H. The matrix H here. So this matrix. So I have, with the notations I've shown you here, how we can get the matrix H, and programmatically we can get like this, simple. Then after that, we form the matrix D, that is the augmented matrix of H and X. This is from the hidden layer or enhancement nodes, and this is for the direct links from the input layer to the output layer. And this is D, and we don't have to worry about anything now. We have all the required matrices and vectors to find the solution. Okay, only one thing we need. Now D we have got, C we have already got as argument to the function, Y we have got already from the parameter list. This I we have to form this I, and I is the identity matrix. So here in this example, this I is the identity matrix of dimension M because it should be compatible to this matrix. Okay, this matrix will be of this one, dimension M by M. Okay, DTD. This is actually transpose of D. Transpose of D, and it is multiplied to the matrix C. Simple multiplication, matrix multiplication. Then we have got beta, and this very beta is the solution that we are finding in this problem. In this much of steps, we have found a solution. After that, we are going for the testing phase. So test data was left apart. Now we are forming the test matrix similar to the train matrix T. Okay, here we are forming the same similar matrix, and we are predicting the value. In case of classification problem, binary classification basically, because that is a simple form of classification problems. So in that case, we have to, in binary classification, we have two classes. Okay, so in that case, we can use sign function. If this value, whatever value we get from this multiplication, if it is negative, then it will be -1, it will give us -1. If it is positive, it will give us +1. So -1 and +1 are the two classes. So in case of binary classification, we can use this function. But if we are using some regression problem, we are solving some regression problem, then we do not have to use any sign. Directly you can use here like this. So now in this case, Y predict is the vector that is the output from the your neural network, random vector functional link network. So what we have got, we had this Y as a vector. Okay, this is the target output, and based on that, in single iteration and single statement, it is like a single linear equation, right? So in this case, with single statement, we have solved the whole problem, and we have got Y predicted. In this program, this is the vector that is giving us the predicted value. This is the target value or original value, and this is the predicted value. Now after that, we can do some we can go for the confusion matrix to evaluate the performance, to get the performance measure like accuracy, AUC, Gmin, or F1, whatever we want, we can go for it. We have ultimately got the predicted result. So this much we have to do, and some other things we have to definitely do to make it a complete package. Okay, but this is the basic thing. So see, this is a very simple algorithm. If you want to research on it, there are so many researches going on. Nowadays, deep RVFL are also available. So, but the concept here is similar. So if you know the basic, then you can go for some advanced algorithms. Then another similar algorithm is extreme learning machine. In extreme learning machine, what we have in case of RVFL, we had these direct connections, but in case of ELM, we do not have these direct connections. We have input layer, we have hidden layer, and we have output layer, and we do not have any direct connection from input layer to the output layer. We have connections from input to the hidden, then hidden to the output. So we do not have these direct links. That is the only difference, structural difference from ELM and RVFL. Okay, so there is the only structural difference we can see here. We have input layer, we have output layer, and we have one hidden layer. From input to hidden, it is fully connected. Then hidden to also output, it is fully connected. And the other things are same. Now, ELM also, we can consider the optimization problem similar to RVFL. In that case, it would be minimum of RVFL, it was minimum of d beta minus y. Then this was a regularized optimization problem for RVFL. Now, if we follow similar kind of approach, then it would be instead of D, we'll have H. Because in D what we had D was H and X. And this is from hidden layer and this is for the direct link. So we do not have direct link. Then ultimately we'll have D is equal to H. So we can directly put H beta here. And like this we can solve in ELM. But we are in this discussion, we are going to see the original approach. So ultimately, in the original approach, it was very simple. What the inventors or authors has done. So this will give us the weight matrix W, random weight. Okay, then this is beta for this link, and after processing this activation function, I mean passing through the activation function in all the neurons of the hidden layer, what we'll get? We'll get a matrix H, and which is equal to the matrix in the notations I have shown you, using W, using activation function, using X, using bias. In this case, bias is not shown here. So all after going through all the process, we'll get H as the output from these neurons. Okay, the matrix H. The matrix H is the output from the hidden layer, and that will be multiplied with the, weights from the hidden layer to the output layer, and we should get Y. It should be equal. So we do not know this. We have got this using the random weights. We know X, we know the weights, random weights, then we know the activation function. And after all these things, till here, we have from here till here, this part we know everything. So after that, after this part, we have got H. That is something like constant. We are not going to improvise anything in H. What we are going to improvise, we are going to find the best possible solution for beta. And beta should be something so that when we multiply H with beta, we should get Y. So this is the equation, simple equation, and we are going to solve this. Now when you solve this is the original version of ELM. When you solve this is a simple equation. So beta is equal to, it should be actually equal to H inverse Y, right? But inverse kahan pe hota hai? Inverse will be applicable only to those matrices which are square, but the edge we are getting here, it is not square, it is of size or dimension given here. So it will be, this edge is, so here xi is how many of how many, this one, it will be of m, size m, and number of hidden layers is L. So the matrix H is of this dimension m by L, which is not square. In some situations, it might be square when the number of input and number of hidden layer are same. In that case, it will be a square matrix. Otherwise, it will not. It is not a square matrix. So basically, we cannot directly find the inverse of H. So that is why there is one technique, Moore-Penrose pseudo inverse. So that gives us the facility to find inverse of non-square matrices. So that is why this plus, actually it is not plus. So I put it as plus. So it should be something like this. So that will give us the inverse of this. So, and when you multiply with the target, so we get the beta value. Okay. So that is what we have to solve in case of ELM, the basic, traditional and classical ELM. And for all the algorithms, I have included the references below. Okay. So this is the paper where you can find, you can study ELM. Then this is the Matlab code. So these things are same. Here we do not have to pass C. When you have, if we use the optimization problem similar to RVFL, then we have to pass C. Otherwise, we do not have to pass C. This part is same. This is also same. Here we are just finding beta using Y and H. And P, I, and B is the function to compute this pseudo inverse. Okay, and this will give us the solution, and it is as simple as that. After that, we can test it. For testing, we do not have to compute that D matrix, okay, directly, because we do not have direct links. So ultimately, we will get the predicted value, and we can use some confusion metrics to find out the evaluation measures like AUC, accuracy, F1, or whatever we want. We can do this one. So in one paper, so this paper, you can find there are some investigations on RVFL's performance. So what are the effects? This paper investigates actually what are the effects of direct links, what are the effects of bias, then scaling factor. Scaling means in the random weights, we might use some different range, maybe 0 to 1, maybe -1 to -1, or maybe 0.5, 0 to 0.5. Those scalings are there. So this is, if you want to explore, you can explore the scaling thing also. And after that, the authors have used these activation functions. These are very commonly used activation functions. So for all of them, they have seen the performance. Okay, they have seen used some 121 data sets from the UCI databases. In this UCI, there are so many data sets that could be used for evaluating the performance of your algorithms. Okay, those are free. You can easily download them. Then in the paper, they have observed that direct links lead to better performance than those without direct links. In case of ELM, we have seen we do not have direct links. That means RVFL should perform better than ELM. And after that, so bias doesn't have any, specific role. Basically, we cannot say that bias can improve or degrade the performance. In some cases, using the bias improved the performance. In some cases, it was not the case. So some other similar methods. So these are very classical methods: kernel ridge regression, least square support vector machine, kernel-based RVFL. So if you understood our concept of RVFL and ELM, then these algorithms will be very easy to understand and implement. So the structures are given here. So we'll not go into details. So the references are here. Then I have used some data set 3, 4, 5, 6, 7, 8, 9, 10. So for 10 data sets, I have evaluated the performance. These are binary classification data set. So these are the algorithms and they perform like this. And for interested readers, these are some references. If you are interested to explore RVFL or ELM or single hidden layer feedforward network that uses non-iterative closed form based solution, and you can refer to them. And the advantages we have seen, advantages of non-iterative schemes or non-iterative algorithms we have seen. So it will overcome these shortcomings of backpropagation. So it is faster. It is always universal approximation. That means it will give always the global optimum solution, not like iterative approaches where we might get stuck in local minima or local optima. Then convergence, slow convergence rate is not there, so it converges to the global optimum, and it is like fixed. Okay, it just have to calculate some matrix inverses. Then sensitivity, we not have learning rate here, so we not have to tune these parameters. So ultimately, it is much more faster than those iterative schemes, and powerful also. Okay, so this is all for today's topic. If you have any questions, you can ask.
So yeah, thank you, Parashjyoti. So the concept was explained quite nicely. So the participant, if you have any question, then you can directly put your question in the session, or you can put the question using the chat box. Okay. So in the meantime, if the candidate are asking question.
Okay, I think we do not have any questions. So yeah.
I think somebody has a question. I think somebody's typing.
In the chat box, I don't see any questions. Okay.
So I think sir lost his internet.
Yeah. Am I audible, ma'am?
Yes, sir. Please continue, sir.
Yeah, Paras sir, can you hear me?
Yes, yes.
Yeah. So sorry, sir. But so can I ask you a few questions?
Yes, yes, sure, sir.
Yeah. So the thing, yeah. So there's one question in the chat box. Let me share this question. The question is what?
Yeah. Does this algorithm works for sequence to sequence task? That means time series data you are asking. No, it is not like LSTM or recurrent neural network. It doesn't have. Those are very advanced. Yeah. If you are asking about time series, so there are some methods. This will work, but you have to pre-process. Not pre-process actually. You have to arrange in a different way. So you have to define some window that will arrange the data set. So yeah, definitely I have used some time series data. So it works. In fact, in one reference, you can visit that. Okay, one of my junior in PhD, this one. So this reference, if you see in this reference, in this paper, they have used time series data for, predicting this COVID-19 spread. Okay, and it was during the first wave of COVID, and somewhat they have predicted up to some precision. Actually, it happened like that to some months, and they have used RVFL only, but along with that, some other techniques were incorporated in their algorithm.
Okay, sir. Can I? So my question is what? So the only structural difference between RVF, ELM and RVFL is the direct link. Is it
Yes,
so, sir?
yes, yes, yes.
Now, if that is the only case, then what? And you saw what you said that RVFL is going to provide more accuracy in most of the data sets. So my question is there any data set for which or the direct link is always going to give us better result?
It is actually we do not have such algorithms which we can confidently say that it will always perform better than the other. In some cases, we might get some better results, but in single data set also we cannot say. If you are using different training for different experiments, different. I mean, suppose you have used some random 30% samples for training, suppose for ELM and RVFL, both the algorithms, suppose same training you have used. For some random, it might give better result. For some random 30, it might give better result in case of ELM. So that we cannot directly say, but in most of the cases, if we if we average it, then we can say on an average, RVFL performs better.
Yeah, so my second question will be not specific to this topic, but it's like what, let's say I have one data and can I assume that this particular algorithm is going to give me better result? Is there any way to determine that this for this category of data, this particular algorithm may give the better result?
Yeah, may
Is there
you
any
can
way
do.
to determine that?
There is no very specific ways for. Yeah, am I audible, sir?
Yes, sir.
Yeah, okay. So we do not have specific ways that directly we can say for this data set we can directly say that this algorithm will perform better. But we suppose if we are using image processing kind of thing, then definitely deep learning nowadays they are working very fine. So very excellent result they are giving. But in that case, we have to feed a large amount of data. If we feed very little data, sometimes deep learning also fail. I am telling you, in some data sets where we do not have sufficient data, in those cases, deep learning cannot outperform these very simple methods. These simple methods are performing better in those cases, in some cases. So for specific data, directly we cannot say because we do not know the distribution of the data, how data are distributed, how much noise are there, how much outliers are there. Those things we do not know beforehand, actually. So for considering the algorithms, we cannot say directly. That is why we have to use some algorithms which gives better average performance.
Yes, sir. And the question will be what the number of hidden layers. Is it what? So we can vary the number of hidden layers, but is there any impact of number of layers on the layers? Or can we determine that this much number of layers is going to what is sufficient for this particular data set?
Yeah, there are some techniques in the literature. If you are interested, I have to search it. I'll forward it. So in some papers or researches, they have shown some techniques how we can find not exactly that amount of hidden layers will give the best result. That cannot be said directly, but some close to the best. Otherwise, in these cases, what we do, we use some grid search. So we use suppose 50, 100, 200, 500 for all the number of hidden layers we check, and whichever is giving the best performance, we select that for the classification task or regression task. So this way we can do for the classical thing. But if you want to, actually, so many developments are already done. So yeah, using even genetic algorithm or PSO, all those techniques also, evolutionary technique also, you can use to identify the optimum number of hidden layers. So those techniques are there.
Okay. Thank you, sir. Okay, so now I will
Okay, hello, am I audible?
Yes, sir.
Thank you. Yeah. So
I
it
think
was
Bharat,
nice
Divya sir has
presentation.
lost connection, I think.
Yeah. Okay. So very good afternoon to everyone. On behalf of the Computer Science and Engineering Department of Sikya National University, I would like to express our deepest gratitude to Dr. Parashjyoti Borah. And today topic was very simple yet very interesting. And it has Dr. Paros has started this discussion by explaining the usage and application area. Nowadays, a lot of presentations and discussions are going on like deep learning, but personally, I didn't know such thing about shallow learning. He also showed Matlab functions, how to implement it, and the relation to extreme machine learning. And he has also provided interesting references, which looks interesting from the title, and certainly we should follow those. And with this, I again thank you, Dr. Parashjyoti Borah. And on behalf of this organizing team, I would also like to thank everyone presented here. And our heartiest thank to Dr. Madhuri Rao, Dr. Sarada Prasannapati, Dr. Divyasundar Das, and our head of the department, Professor Devati Mishra, for organizing this webinar. So thank you everyone, and I wish everyone a happy weekend. Thank you again, Dr. Parashjyoti sir.
Thank you for having me, giving me the opportunity to interact, and it was very nice to come back again to SOA in some ways. Anyway, so I hope all the best to all the students. So and hope to get associated to SOA in future. Okay, thank you all.
See you. Thank you.
Okay, see you, sir.
Thank you, sir.